Hello students, today we're going to talk about common logarithms. I'm going to talk about what they are, what they do, what they look like, but I also would like to talk about why bother with them. Why bother with logarithms at all? What exactly are they? How am I going to use them in real life? What's their history? So we're going to talk a little bit about all that stuff, but let's just dive into the basics, the stuff that's going to help with the homework first, right? So logarithms, as you guys have been dealing with a lot here, you know that every logarithm has some sort of base down here, some number, little tiny number under the log before this more large number, and that's equal to some power. So this base here is sometimes not written. Sometimes you'll see a log that just looks like log, and then you'll have your number, and there's no base. Like, what gives? What's up with that? That's because when there's no base written, you are dealing with a common logarithm. It has a base. That base is just invisible. All right. So let's look at what a common logarithm actually is. But first, I want to show you when you're looking at a calculator, and some of you may have found this out already. When you're trying to do logarithms, maybe a few of you pulled out your calculators at home and you said, "Oh, we have a log button. I've seen a log button on my calculator before," and you try to use it on your homework, and it just simply has not given you the right answer. Well, that's because all of your calculators are programmed that when you push that log button, it's going to give you a common log. So if we were working in base 2 or base 3 or base 7 or whatever, the calculator is going to be useless, at least until a further lesson. But yeah, that's something that you got to look out for, but at least now you'll know why your calculator has been failing you, right? This is your common logarithm. The base of a common logarithm is always 10. It's always 10. This 10 here is invisible. It's implied. It's not written, but it's there. We've seen a couple of other mathematical expressions and terms and operations that sort of imply numbers like that. One of the more common that you'll see are square roots, right? If you've got the square root of 36, well, whenever we're doing a cubed root, say like the cubed root of 125, we have a 3 there. We have a 3 that's right here, but when we do a square root, there's nothing there. That's because we do have a 2 there. It's just that 2 is kind of implied. It's implied. We don't need to write it. It's assumed by virtue of you having written this radical, this symbol, right? So it's the same thing with a logarithm, that when the base is not written, it is assumed to be 10, right? So you can easily write a log with a base 10 and say like base 10 of log base 10 of 8 is equal to some x, and if we were going to transfer this into exponential form, that would be 10 to the x power is equal to 8, right? But this sort of way of expressing something with a 10 base, it doesn't have to be written this way. We can save ourselves some time, simplify it a little bit, and say log of 5 is equal to y, and the exponent, the exponential equation, is still written the same way. It's still 10 to the y equals 5. It's just that we don't have to write it because we just use it so often. It would just add more time to our assignments if we're having to write 10 so much. Okay, so like why? For the love of Pete, why? Why are we doing this? Why is 10 so common? Why is it so used? And the real heart of this issue is just kind of, it's what number system are we using? And the reality of the situation is that you and I, since birth, have been practicing, well, not birth, but I guess, kindergarten or first grade, have been taught to use a decimal number system. And what does that mean? You know what decimals are. It's when you put the little period on your number and have numbers after that, right? But no, when I say a decimal number system, I am talking about a base 10. What is the word deci? What does the prefix deci mean? Well, you know what hex is. Hex is 6 and oct is 8. Well, deci, see, it's 6, 8. Deci means 10, right? A decagon, a decigon, whatever, is 10 sides, right? So we're saying that we work in a base 10 number system. And what does base 10 number system mean? Well, it means that for every placeholder, like if I write a number, 327, each placeholder, there's one here, the ones place, the tens place, the hundreds place, each of those has 10 possible symbols that can then go in here and represent a different number. Our 10 symbols are, well, I forgot 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then once we get to 9, we can't go any higher than that and achieve a new value without creating another place. So we go from 0 to 9, we run out of room, well then we just add another place value and start at 1 again. And then you'll have 11, 12, 13, 14, 15, so you run out of place, you go and step it up a notch. And each time you put a new placeholder in there, you've grown by a factor of 10, which is kind of important to this concept of growth that we're talking about, okay? And that is really the heart of this issue of why we're using logarithms at all. What are logarithms? Logarithms are exponents, and exponents are going to show you growth, especially over periods of time. The most common way that you and I in our regular lives are going to deal with logarithms is in the form of interest rates, finance, banking, stocks, and stuff, because that's just the more common thing, that every portfolio or principal value of money, if you have it in the bank, is accruing interest, and it's going to grow over time according to some logarithm, some exponential growth, right? And that's really the most practical way. That is, we're going to explain natural logarithms in the future, but more specified, more scientific ways of using logs is in base 10. You'll notice that in astronomy and in chemistry and in geology and any science, they're going to use the 10th, or not the 10th power, but the 10th base. You've heard of scientific notation, where you have like a 1 times 10 to the, I don't know, 10th power or something. This is scientific notation, and this right here, this is a common log. This is a common log. This is what we're using right here. In chemistry, you have Avogadro's number, which is like 6.02 times 10 to the 23rd power, right? And then you have in geology, you've got Richter scales. Richter scale, that's what we use to measure the magnitude of earthquakes. And if we have a 9.5, that's the most powerful earthquake ever registered, ever recorded by humans. That's actually what it means is 10 to the 9.5. I can't remember the unit. It was like joules or kilojoules or something of energy, and that is just an enormous number. But then at the same time, if this exponent is really low, it's not going to be very big. So like 10 to the first power is just 10, right? And 10 to the 0th power is just 1. But 10 to the 23rd power, if we're looking at the Avogadro's number, that is a 1 with 22 zeros. 22 0. I'm not going to do all of them, but you get the idea. That is enormous. Now, logarithms take us away from dealing with this enormous number, and now we're only dealing with a 0 or a 1 or a 23, and we can use our logarithm properties to manipulate these numbers that are just too large to fathom, because human beings really are just terrible at imagining large numbers. If I wanted to tell you how many molecules or atoms were in the universe, it would just be this. It would be 10 to the 80th power. It's something like that. I mean, that's the current scientific estimate. But is it easier to deal with 10 to the 80th power, or is it easier to deal with 10 or 1 with 79 zeros after it? That makes calculations just so difficult. So that's really what logarithms are for, and that's why the base 10 of the logarithm is used more often than any other, because for every one number you increase in this exponent, you're adding a placeholder in our decimal number system. And okay, why do we use a decimal number system? Well, the answer to that's like really simple. It's because we got 10. I know these are terrible hands, but we've got 10 fingers. Everyone when they're learning to count learns to count on their hands, and so I guess we figured that it was easy to have just one corresponding symbol for each finger on our hand. Okay. So I hope that's interesting to you. I hope it makes a lot of sense. But I want to go a little bit further. I want to talk a little bit about the history of logarithms and talk about this really interesting guy. His name was John Napier. He was a Scottish mathematician who just has the most, I want to say interesting, but it's definitely interesting, but it's definitely a ridiculous biography. This guy was crazy, verifiably insane. He was a genius, but he was just a psycho when it comes to the way that he lived his life, which all geniuses are insane to some degree, but man, this guy really takes the cake. So he invented logarithms, and he invented logarithms for precisely the reason I was just talking about, is that he hated doing calculations with large numbers, and he wanted to find a way of manipulating large numbers without having to basically waste all this paper and take all of his time, and so he invented logarithms. He also, you're going to love this about him, he hated fractions, just like most of my high school students. He hated fractions, hated working with them, and he was the one who popularized writing decimals. He would rather write 0.5 than he would write 1/2. So this really gained popularity because of this guy right here. So if you love working with decimals and you hate fractions, you're going to get along great with this guy. But if you don't like decimals and you're like me and you don't like really large numbers, or you don't like using logarithms, then you're also in good company, because this guy had a whole lot of enemies for some really crazy reasons. Like I said, he did a lot of crazy stuff. This guy was thought to be some sort of like occult practitioner, because of he was an alchemist. He spent a lot of his time trying to turn lead into gold, trying to discover the secret to immortal life using science, or I guess the best science at the time. He tried to come up with formula that would bring people back from the dead, and that's not even the most interesting part about this guy. This guy, he had a pet rooster that he carried around with him all the time, and on a couple of occasions, he actually used this rooster to fight crime, solve crime, catch criminals and stuff, and he did it in really creative ways. He also kept with him a box in which he kept spiders in this box. I don't actually know why he did that, but some people assume that he kept spiders around as some witchcraft familiars that this guy had. He came up with the most ridiculously creative solutions to problems. He had a granary, and he was tired of pigeons coming into his granary and stealing all of his grain. And so his solution to that was to get all of these pigeons kind of drunk. No joke. This guy, what he did was he laced all of his grain with alcohol, waited for the birds to come and eat his grain, and then when they were drunk, they would pass out and fall on the ground, and he captured all of these birds. This guy was a crazy genius. This is a light bulb here. But anyway, if you're interested in math history and you want to know about the guy who invented logarithms, definitely look into him. He's just a psycho, and he's a pleasure to look at. Anyway, I hope that kind of gave you a different perspective on the math that we're doing here, and helped enlighten you about why we're using it at all. Anyway, I'll see you in the next video. We're going to talk about some slightly more mathematical procedures. Okay, well, I'll see you in the next video, guys.